Good morning. Welcome to the 2018 AP Chemistry FRQ question 2 walkthrough. We're going to start with A and go all the way through. I'll make a point of noting what will not be on the 2020 AP Chemistry exam as I go, however. Question 2 starts with a chemical reaction that says 2NO gas plus O2 gas gives you 2NO2, which is going to be very important for part A. So let's go ahead and put that in. 2NO gas plus O2 goes to 2NO2. And it says the student investigates the reactions of nitrogen oxides. One of the reactions in the investigation requires an equal molar mixture of NO and NO2, which the student produces using the reaction as represented above. A particle level representation of the equal molar mixture of NO gas and NO2 gas in the flask at the completion of the reaction between NO and O2 is shown in the box to the right. In the box below on the left, draw the particle level representation of the reactant mixture of NO gas and O2 gas that would yield the product mixture as shown in the box to the right. In your drawing, represent oxygen atoms and nitrogen atoms as indicated below. It has colored and shaded. I use different colors, brown and red. So there are a few ways to go about this, but the easiest way I find is to look at it and go, okay, let's work this reaction backwards. First things first, we have NO, which is the brown-red combinations. Okay, that isn't a product. So any NO we have has to be left over from the reactants. So any NO we have here, which I'm going to label with this, these 1, 2, 3, 4 molecules of NO had to be there originally. So anything that's left over had to be there originally. So let's just draw those in. 1, 2, 3, 4. 1, 2, 3, 4. And there you go. There's your NOs that we traced over. On the other hand, we have, let's count out our NO2s. We have, I'm going to label these with letters, A, B, C, D, or 1, 2, 3, 4 NO2s. Now, you can do this again one of two ways, or one of many ways. But the easiest way I found is to work your stoichiometry backwards. We have 4, or A, B, C, D, NO2s. So for every 2 NO2s, we should have 2 NOs and 1 O2. So if we have 4 NO2s, which we do, 1, 2, 3, 4, that'll give us 4 NOs and 2 O2s. Again, that's just stoichiometric ratios. 2, 1, 2, 4, 2, 4. In fact, I'm going to write that out just so you can see it. 4, 2, 4. We'll maintain the ratios we had previously. So let's step it back. Go ahead. So I have 4 NO2s, which means I should have 4 NOs. 1, 2, 3, 4. 1, 2, 3, 4. And I should have 2 O2s. 1, 2. Now, there are some other ways you can go about this. But let's talk about how we check our answers, and then we'll talk about those other answers. First things first, count your number of molecules. You should have the same number of molecules on both sides. Or more accurately, count your atoms. You have 1, 2, 3, 4, 5, 6, 7, 8 nitrogens. 1, 2, 3, 4, 5, 6, 7, 8 nitrogens. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens. Excellent. A very common other way to go about this is to go, okay, each of these NO2s had an extra oxygen added to them. So if I take one oxygen from this one oxygen from this one oxygen from this one oxygen from this one. I take those 4 oxygens, set them aside. I have 8 NOs, and the 4 oxygens will combine together to make the 2 O2s. However you go about it, that's on you, but these are 2 ways to think about it. The advertised and recommended way is to go through the stoichiometric ratio. B states, the student reads in a reference text that NO and O2 will react as represented by the equation below, this one here in green. Thermodynamic data for the given reaction is given in the table below the reaction. This thermodynamic data hasn't really been covered and won't be on the 2020 exam, but we're still going to go over it because some of it has, and it's still a solvable problem. We've talked about delta H, delta S. We haven't, and delta G we've barely touched on, but we can still do some of the questions. B1 says calculate the value of the equilibrium constant K for the reaction at 298. Now, we've touched on this briefly, but a far easier way to go about this problem is you look at your equation sheet and you go, okay, which one has a piece of data that we have and K. And if you look through your equation sheet, and you'll eventually find that there's a single equation that has data we have and K. And that equation is delta G standard equals negative RT ln K. This equation is the only equation that both relates delta G and K, and it works off information we have. Now, going through this and solving for K is a little difficult, so I'm going to do the algebra on the screen. We want to solve for K. We need to have a K value. So I'm going to solve this algebraically. First things first, let's get this RT to the other side. Divide by RT, divide by RT, cancels out. Gives me, I'm going to flip this around, natural log K equals delta G negative over RT. Quickest way to undo a log, raise both sides to the base. So I will then get this to cancel out, which gives me K equals e to the negative delta G over RT. If I go to the next step and go ahead and plug in our numbers, all we need is E, which is a constant given by your calculators, negative delta G. Be careful, this is in kilojoules, but R for energy is 8.314 joules. So we need to convert this kilojoules right here to joules, which would be multiplied by 1,870 divided by 8.314, which is R, times T, which is 298. Put this in your calculator, remembering your parentheses and being careful with that, and noting that we're going to go to 2 decimal spots because there are 1, 2, and we are multiplying. Gives us 0.70 is our K value, which tells us very definitively that the reaction in this particular case is equal, or the reaction in this particular case very much is close to not favoring either side, but does favor the reactants. That's A and B1. Let's talk about B2. Part 2 reads, if both the PNO and the PNO2 in the vessel are initially 1 atmosphere, will PN2O3 at equilibrium be equal to 1 atmosphere? Justify your answer. So, again, many ways to go about this. Let's go through a couple. First, you could be like, okay, well, if it's an equilibrium reaction, it means we can set up an ice table. This would be 0.1 minus x, 0.1 minus x, 0 plus x, so which would give you this setup. The only way that x equals 1 is if the reaction goes to completion. All of these reactants disappear and become products. That is the only way you're going to get 1, because that's as low as this can go. That's as high as this can go. So if the reaction would go to completion, yes, that would be true. But since this is an equilibrium reaction, can't go to 1. If you don't like that, doesn't make sense to you, you can remember that in the previous problem, K equaled 0.7. K equaling 0.7 means that the reactants are slightly, but still favored, meaning that the products are not going to be the entirety of the reaction. This reaction does not go to completion. It will not reach 1 because you'll have more reactants than products. Since the reactants both started at 1, the products can't be 1. Alternatively, having a product value of 1 and reactant values would then be 0, which would give you divide by 0 error. Doesn't quite work out. So 2, no, the pressure not equal 1 atmosphere, and then you have to justify using one of the justifications I just talked about. C, the student hypothesizes that increasing the temperature will increase the amount of N2O3 gas in the equilibrium mixture. Indicate whether you agree with or disagree with the hypothesis. Justify your answer. This goes back to the data table we were talking about. And unlike the delta S, which we don't know anything about, and the delta G, which we kind of know some things about, but not really, delta H we've talked about. Delta H explicitly tells us if the reaction is endo or exothermic. As a quick refresher, if delta H is positive, it means heat is a reactant. It is added to the reaction mixture. It is absorbed by the reaction. If it is negative, it tells us heat is a product. It is given off. Combine this with our knowledge of Le Chatelier, and it becomes very clear what our answer should be. This is negative, so this means that heat is a product. Since heat is a product, increasing the temperature is just in effect increasing the products. By increasing the products in any reaction, you shift the mixture to the opposite, to the reactants. Adding reactants shifts the products, adding products shifts to reactants. That's kind of the essence of Le Chatelier. It always moves to reduce the amount of stress on the situation. So by adding heat, we will remove N2O3 by shifting this reaction towards the reactants. So we have to disagree. A more official way of saying that would be, because the reaction is endothermic as indicated by a negative delta H value, increasing the temperature of the reaction will favor the formation of the reactants, because heat in an exothermic reaction is a product. And then, according to Le Chatelier's principle, or some other justification. But there you go. There is B and C on to D. D is the standard skeletal structure question that has been on every AP Chem exam for the past few years and has been frequently practiced. It says the skeletal structure of the HNO2 molecule is shown in the box below. Complete the structure, include any lone pairs. There is two ways to really draw this. The way that you're traditionally taught, or the way the AP exam often will give its answers. Let's go through both. First things first, when asked to do Lewis structure, figure out the Lewis dot diagrams for everything. So hydrogen has 1 dot, oxygen has 6, nitrogen has 5, oxygen has 6. Once you have those 6, you can move them around as necessary to make your drawing prettier, or you can just connect the dots to make it sense. In order to have a complete structure, all molecules must be connected, and all lone pairs must have a partner. So once you have it, just start connecting the dots. Hydrogen is next to the oxygen, so they clearly will have to connect. Oxygen's next to the nitrogen, clearly will have to connect. Nitrogen's next to the oxygen, they'll also have to connect. And then you have these 2 unpaired lone pairs left over, so just pair them up. which gives you a double bond. Now this is messy, but acceptable. If you are a bit of a neat freak like I am, what you'll inevitably end up doing is redrawing with cleaner bonds, giving you something that looks more like so. And there you go. The AP Chemistry exam, however, will typically show paired dots for each thing. And the only difference between this and these structures is that instead of using lines, you'll just put pairs of dots in the middle to represent the bonds that are shared. And in the case of a double bond, it's two sets like so. Same idea, same matchup, same answer, just a slightly different way of expressing it. I personally prefer connect the dots and then straighten it out, but whatever works for you. Part 2 asks you to identify the hybridization on the nitrogen. No matter how you draw it, you can look at it and go, okay, how many ligands, how many regions of electron density do I have? How many things is the nitrogen connected to? And over here, you've got the one oxygen. Over here, you've got the other oxygen. And up here at the top, you've got this lone pair. So there's 3 things. And over here, if I don't screw up my drawing, I forgot the lone pair. I'm so sorry about that. You still get the same thing. 1, 2, 3. 3 ligands. Always and forever be 3 things it's connected to will be sp3. The way I will typically do this is I'll start with S, 1, P, 1, P2, and I'd go to P3 and then D, D1, D2. But in other words, this is sp2 hybridized. So your hybridization in this case is sp2. And there you have it, on to E. Everything from this point on will not be on the 2020 AP Chem exam. Section of text that says, to produce an aqueous solution of HNO3, the student bubbles N2O3 gas into distilled water. Assume that the reaction goes to completion and HNO2 is the only species produced. Lots of extra words, nothing particularly usefully made. To determine the concentration of the HNO2 aqueous in the resulting solution, the student titrates a 100 milliliter sample of the solution with 0.100 molar KOH aqueous. The neutralization reaction is presented below. That's a very important reaction, so let's write that down. It's HNO2 aqueous plus OH minus aqueous, telling us this is an ionic or net ionic reaction. Goes to NO2 minus plus H2O, liquid aqueous. The following titration curve shows the change in pH of the solution during the titration. I've labeled the key point. We'll talk about the rest of it in a bit, but right now I've labeled the key points. E1. Use the titration curve and the information above to determine the initial concentration of the HNO2 aqueous solution. Okay. So there's a lot of superfluous information here. Let's throw that out and focus on the key points. We want to find the concentration of the HNO2. We know it reacted via this reaction. And based on our graph of titrations, we know that right here at 20 milliliters, which is your equivalence point, the moles OH minus equals the moles HNO2. Okay, that's the definition of an equivalence point. So if we can find out how many moles of NaOH we added, or KOH we added, we can find out how many moles HNO2 we have, and then moles per volume is molarity. Awesome. Let's break that down, go through each of those steps one at a time. First things first, how many moles of OH should we have? Well, we have 0.100 moles per liter. And we added 20 milliliters, or 0.020 liters. If you can't do that math in your head, 1 liter is 1,000 milliliter, and we added 20 milliliters at the equivalence point. And notice how I did this one backwards. It's either way will work. If you want to start with the 20, work your way forward. If you want to use the 0.01, work your way backwards. Whatever floats your boat, as long as your units cancel and leave you with only moles left behind. Awesome. So if we do that math out, we find that there is 0.0020 mole KOH. And we know that because of this reaction, there's 1 mole HNO2 per 1 mole OH. If you'd prefer to think of this a different way, 0.0020 mole KOH neutralized (100 milliliters HNO2). These are then equivalent. They're equal to each other, which means I can set up this ratio right here and then convert it over to my next spot. However that works for you in your brain. Regardless, the moles of KOH based on this chemical reaction, because it's 1 to 1, tells us this mole KOH is also your mole HNO2. Okay? If these reactions weren't 1 to 1, you'd have to do an extra step where you convert it. Like, for instance, if we were talking about KOH plus H3PO4, there would be 3. So for every 3 moles of OH, you'd have 1 mole HNO2, and you'd have to go through the stoichiometry. It'd just be an extra tack on here. Let's do this in brown because it's not actually part of the process, just a theoretical. In this case, it would be 3 mole KOH is 1 mole H3PO4. That's our theoretical hypothetical example only, but for this case, it's a 1 to 1 ratio. And look, 1 to 1 cancels out. The only issue here is that I have this in 100 milliliters, which I need to convert to liters. Again, you can move the decimal if you're comfortable, or just add an extra step. And do that math out, and you should get 0.020 molar HNO2. And there you go. That is how you find the concentration. E2 tells you to estimate the value of the pKa for HNO2. So, how do we find the pKa? Well, one of the nice things about pKa and titration curves is that the pKa occurs at the half equivalence point. We said the equivalence point is at 20, based on the sharp rise. So the half equivalence point would be halfway to that point, or when half of the HNO2 is reacted. Half of 20 is 10. So we come here, we look at this, and okay, we look at the pH value, and at the half equivalence point, and only at the half equivalence point, the pKa will equal the pH. So you look here, we go across, and we go, okay, pKa is somewhere between 3 and 4. Use your best judgment. For me, I look at this and go, okay, it's slightly under halfway. I eyeball it. So call it like 3.3 or 3.4. Whatever you choose. And it doesn't even ask you to justify in this case. If it did, you could say the value of the pK, the value of the pH equals the pK at the half equivalence point, which is at 10 milliliters. So therefore, the pH value at 10 milliliters is about 3.3, 3.4, which means the pKa is about 3.3, 3.4. F is dealing with half equivalence points and species present. It says during the titration of after volume is 15 milliliters is added. So when you're here, which species, NHNO2 or NO2 minus, is present at a higher concentration in the solution? Justify your answer. So really what it's asking is, do you have more reactants or more products? And again, we go back to that half equivalence point. At the half equivalence point, the amount of HNO2 you have and the amount of NO2 you have, or the acid and its conjugate base, are equal. Before that point, you have more weak acid. After that point, you have more weak base because of how it reacts. You've only reacted very little here, and you keep reacting more and more and more until half of it's gone. And after that, more than half is reacted. So at 15, you're past the equivalence point. You're past the half equivalence point, which means that you have more NO2 than you do HNO. And a justified sentence might be something like, you have more NO2 minus. The titration is past the half equivalence point, therefore there will be more conjugate base present than acid. Just definitions of half equivalence points. And that is 2018 AP Chemistry number 2.